Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is ladder logic documentation. Our objective is to learn how to properly document a ladder logic diagram. We'll learn to comment functional blocks, number rungs, number wires, number terminals, identify devices and associated contacts, and perform numerical cross-referencing for logical elements in mechanically interlocked devices. Additionally, we'll discuss proper grounding and circuit protection practices. This lecture operates under the assumption you have watched the basic ladder logic lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Recall that ladder logic diagrams make electrical connection and function easily readable and apparent to those practiced in their use. As the ladder logic diagrams we examine increase in complexity, it is often necessary to provide guidance to their interpretation. Documentation allows a reader to reference specific rungs, wires, terminals, devices, and functional blocks, as well as see how related rungs affect each other. Not all the skills demonstrated in this lecture are universal in nature, especially wire numbering, and for this reason, I go to the trouble of presenting alternative techniques. If your employer uses a different technique entirely, I'm urging you to learn and use that technique to the exclusion of all others. This being said, the documentation skills and techniques as presented in this lecture are ordinarily commonplace. First and foremost, a ladder logic diagram is only useful if it can be properly interpreted. It is for this reason computer programmers comment their programs. Designers can hand off the diagram to a technician, and the technician can take it from there. Additionally, if a system must be redesigned, the comments and documentation remind the designer of the intended purpose. Ladder logic documentation can be as simple as annotating the description of a particular functional block on the right-hand side to whatever degree of detail necessitated. Note that I've identified the top group of rungs as those that control the hydraulic actuator. The middle group of rungs control the motor-driven pump, and the bottom group of rungs perform protection and diagnostic services. The purpose of particular functional blocks with easy-to-interpret descriptions makes this ladder logic diagram ever so slightly more understandable. Beyond this simple functional division, this ladder logic diagram may seem to be an incomprehensible soup of rungs, devices, and wires to those unpracticed in their use. Keep in mind, the title of this lecture is Ladder Logic Documentation, and I am not asking you to interpret this particular ladder logic diagram. All we're going to do is to learn how to properly document it. Later lectures on pumping circuits will make use of a derivation of this particular diagram and discuss it in great detail. For starters, we need to number the rungs. Let's start fresh and remove the functional block descriptions. Rung numbering is easy. Each rung is given a number starting at the top and working our way to the bottom. Rung numbers appear on the left. Rungs are defined as complete paths from the left to the right. Note that the holding contacts CR1A and P1 are both their own individual rungs. This particular ladder logic diagram has 8 rungs. Rungs 1 through 3 serve to control the hydraulic actuator. Rungs 4 to 5 control the motor-driven pump. Rungs 6 through 8 serve diagnostic and protection purposes. Rung numbering allows a technician to reference a specific conductive path from left to right. Now we need to number the wires. This is where things get interesting, because there are a lot of different methods of doing so, 2 of which I'll show here. First, don't think of them as wires, but rather nodes. Recall that a node is a common point of connection. Note that the right terminal of the e-stop is connected to a bunch of other devices. This is a common point of connection, and all devices hooked to this single pool should have the same voltage with reference to another point. That's really the purpose of wire numbering. Let's start with a fresh slate. Method 1. Method 1 starts with wire number 1 being the left upright. Everything attached to the left upright is given wire number 1. Notice I'm circling the wire number. There's really only one device attached to the left upright, the left terminal of the e-stop. Method 1 then has us skip the contents of the first rung and jumps to the right upright. all devices attached to this common connection are assigned the wire number 2. Note a number of different devices all have wire number 2 leading from them. I must again emphasize that wire numbering is better thought of as node numbering. A voltmeter from wire 1 to the terminal of any device hooked to wire number 2 should read the full pilot voltage. Now, method 1 has us return to our earlier point of departure and then assign numerically sequential wires from here. Everything connected to the right terminal of the e-stop is assigned wire number 2. This is a common point of connection. Now, method 1 has us move left to right and then top to bottom, filling in all the wire numbers as we go. Note holding contact CR1A in rung 2 has wire numbers 4 and 5 leading to it, since it is a common point of connection to wires sequentially assigned left to right, top to bottom in the rung above it. Similarly, note that holding contact P1 in rung 5 has wire numbers 7 and 8 leading to it, since it is also a common point of connection to wires sequentially assigned left to right, top to bottom in the rung above it. All in all, it looks like we top out at wire number 14 for this particular ladder logic diagram. Note this is 14 wire numbers, not 14 wires. As I previously stated, wire numbering is better thought of as node numbering. A lot of wires lead from node 2 and 3. However, they're all connected to the same place. Method 2. Let's start with a fresh slate. Before we move on to numerical cross-referencing and terminal numbers, let me briefly introduce an alternate method of wire numbering you may run across just to confuse the heck out of you. This isn't my favorite method because method 1 clearly identifies two very important wires, 1 and 2, as the left and right vertical uprights. Method 2 is a little sloppy in that there is no predicting what wire number the right vertical upright receives. This being said, a lot of manufacturers use this scheme, and it's something you should be aware of. Method 2 starts similar to method 1. First, start with wire number 1 being the left upright. Everything attached to the left upright is given wire number 1. Again, there is really only one device attached to the left upright, the left terminal of the e-stop. Method 2, however, does not skip the contents of the first rung and continues assigning wire numbers left to right until it reaches the right vertical upright. Once the right vertical upright is reached, all devices attached to this common connection are assigned this number. In this case, the wire number is 5. Method 2 then continues as did method 1, assigning wire numbers left to right, top to bottom. Notice we still top out at 14 wire numbers, only wire 5 is now the right vertical upright instead of wire number 2. I know, this method drives me crazy too. There's no way of predicting which wire number the right up rail receives in advance. It all depends on how many devices are in the first rung. For this reason, I prefer method 1. The left upright rail is wire number 1, the right upright rail is wire number 2. Wire numbers are then assigned left to right, top to bottom. This is the method I ordinarily prefer, and the method you'll see me use during the course of this lecture series. Before we continue documenting this ladder logic diagram, we need to perform a brief review on terminal numbering. Recall that control relays and contactors are characterized by a coil and associated contacts that switch their activated state when the magnetically linked coil is energized by pilot voltage. An 11-pin ice cube relay is ordinarily characterized by the coil from terminals A1 to A2 and 3 single-pole double-throw transfer switches where the first digit identifies the particular switch and the second digit identifies its deactivated state. A second digit of 1 indicates that it is the common servicing both sides of the transfer switch. A second digit of 2 indicates that it is the normally closed side of the transfer switch. A second digit of 4 indicates that it is the normally open side of the transfer switch. When the coil of this relay is energized, the normally closed side opens and the normally open side closes. Alternatively, a mini contactor control relay may feature electrically isolated single-pole, single-throw switches like this one. These control relays are ordinarily characterized by a coil, also from terminals A1 to A2, and 4 single-pole, single-throw switches, where the first digit identifies the particular switch, and the second digit identifies the switch's deactivated state. A second-digit pairing of 1, 2 indicates it is a normally closed switch. A second-digit pairing of 3, 4 indicates it is a normally open switch. When the coil of the relay is energized, the normally closed switches open and the normally open switches close. Similarly, a contactor is characterized by a set of primary contacts that close when the magnetically linked coil is energized by pilot voltage. When the coil from terminal A1 to A2 is energized by pilot voltage, the primary L2T contacts would close. The L2T primary contacts are not included in the ladder logic diagram, but rather the primary schematic. Contactors sometimes feature an auxiliary pilot contact from terminals 1, 3 to 1, 4 that changes to its opposite state when the coil is energized. If the application necessitates additional functionality, an auxiliary contact block can be utilized that includes other auxiliary pilot level contacts. When the coil is energized by pilot voltage, these auxiliary contacts would also change to their opposite state. Note that the first digit in the terminal numbers for a contactor, pilot contacts, identify a particular switch, and the second digit pairing indicates that particular switch's deactivated state. A 1, 2 switch is normally closed. A 3, 4 switch is normally open. In keeping with this theme, limit switches, push buttons, and other switches ordinarily number terminals such that the normally closed side is terminals 1, 2, and the normally open side is terminals 3, 4.